We're going to start chapter 4.1 and 4.2. 4.1 is on solute concentrations, so we think of solution concentrations. And then we're going to talk about electrolytes while we're talking about solutions. We're going to get into net ionic equations, where net means that we only show what changes. And then we'll get into a specific type of net ionic equation called precipitation reactions. Okay, solute concentrations. Any concentration term is a statement of the amount of solute per a given amount of solution. The way we measure the amount of solute and measure the amount of solution is what would be different in any concentration term. The main concentration term that any chemist uses is called molarity, which is abbreviated as capital M bar, and it refers to the number of moles of solute per liter of solution. Now, since we are going to be using our units to set up all the calculations involving molarity, we need to identify again that molarity, big M bar, means moles per liter. So if you're given big M bar, identify that means moles per liter. If you're after big M bar, recognize you're after moles per liter. So as an example, if we have a sample of vinegar, which is found to contain 18.9 grams of acetic acid, that's essentially the active ingredient in vinegar, in which you smell when you smell vinegar, and 341 milliliters of the vinegar, calculate the molarity of the acetic acid in the vinegar. Okay, we're using our units, and that begins with step 1. What are we after? Big M bar? No, we're after moles per liter. Moles of the acetic acid, which I'm going to represent as AA, per liter of the vinegar, or liter of solution. That makes sure that for step 2 we start correctly. If you finish with 1 unit per another, then you're starting with 1 unit per another. And I have 2 single pieces of information, the grams of acetic acid and the milliliters of solution. Which do you think goes on the top and takes us to moles of acetic acid? And that would be the grams of acetic acid. If you get stuck on the top, ask about the bottom, which should take us to liters of solution, and that would be the milliliters of solution. Okay, we need to get out of both of these units. Let's start with the numerator, so out of grams of acetic acid. And now comes the big question. Again, getting this far should be pretty much an easy question, so pretty much straightforward. And now we ask, can we go straight from grams of acetic acid to moles of acetic acid? Yes, there's our most common calculation in all of chemistry. Then, out of milliliters of solution, can we go to liters of solution? That's a simple metric conversion, so yes again. Note all units cancel, but moles per liter. Now for the numbers, we see the formula of acetic acid, so I have 1 for the first hydrogen, 2 times 12 for the carbons, 3 times 1 for the other 3 hydrogens, and 2 times 16 for the 2 oxygens, which adds up to 60.0 grams per each mole. And 1 milliliter 10 to the negative 3rd liters. And when I put this on my calculator, I come up with a 0.924 molar solution. Or we can write this in scientific notation, 9.24 times 10 to the negative 1. Now, if you're given the molarity concentration term, again, we need to identify what it means. That it means moles per liter. And so, essentially, molarity takes us from moles to liters. So from a given number of moles or mass of your subject to a volume of solution, or from liters to moles. So from a given volume of solution to the number of moles or a specific mass of your solute. We'll know which one we're using when we get there, so don't worry about knowing which one ahead of time. Let's do a couple examples. We're asked how many milliliters of a 0.789 molar acetic acid solution are needed to provide 0.475 moles of acetic acid. Okay, again, you're given a concentration term of molarity, and we really need to identify what does that really mean. 0.789 moles of acetic acid per liter of solution. So it might be a good idea to pull out that concentration term so that we can see it for the tool that it is, the conversion factor. Then we'll start step 1. We're after milliliters of solution. Step 2, well, now it's obvious which number has a single unit, at 0.475 moles. At 0.789 big M bar, we now recognize is actually moles per liter, 2 units. And now, step 3, out of moles of acetic acid. And again, getting this far should be pretty straightforward. Now comes the big question. Can we go from moles of acetic acid to milliliters? No, but right in front of us we can see that moles will take us to liters. And we know that we can go from liters to milliliters with a simple metric conversion. And now for the numbers, that 0.789 goes with the moles of the acetic acid. And 1 milliliter, 10 to the negative third liters, base 10 number, still going with the base unit. So 0.475 divide 0.789, divide 10 to the negative third for 602 milliliters. Now let's go the other way. How many moles of acetic acid are in 602 milliliters of a 0.789 molar acetic acid solution? Now look at this problem and look at the last problem. Can you see what the answer is? I think you know. But if you don't, let's calculate it. Step 1, we're after moles of acetic acid. Step 2, we're going to start with that 602 milliliters. Again, that big M bar is 2 units, and we can't start with 2 if we finish with 1. Step 3 begins by getting out of milliliters. And here comes the big question. Can we go straight from milliliters to moles? No, we see we're going to get to moles from liters. So first from milliliters to liters, and then from liters we can go to moles. 1 milliliter, 10 to the negative third liters, and that's 0.789 with the moles of acetic acid and 1 with the liters of solution. And that gives you that 0.475 moles. So essentially these were same question but going in 2 different directions. One from moles to volume, one from volume to moles. Like I said, we'll know when we get there which conversion factors we need to use, so we don't need to worry about that ahead of time. And I hope by now you're already loving those units. Okay, on to electrolytes. While we're talking about solutions, electrolytes are substances that form water-based solutions that conduct electricity. Now, what conducts electricity are ions, so we need mobile ions in solution. Now there are 3 types of electrolytes. We have strong electrolytes, and to be strong, they're going to form ions at high concentrations. We also have weak electrolytes. Let me get to that in a second. Strong electrolytes would include strong acids and strong bases and highly soluble ionic compounds like table salt. And we'll talk about strong electrolytes when we talk about strong acids and bases in a future chapter. But all these form high concentrations of ions. Weak electrolytes are still electrolytes, but they're not doing a good job of conducting electricity because they form relatively low concentrations of ions. Examples would be weak acids and weak bases, and we'll talk about those when we get to that chapter on acids and bases. And limited solubility salts. Salts is a general term referring to ionic compounds. So there are low solubility salts which form some ions, but again, not very many. And then lastly, we have non-electrolytes, and these aren't going to form ions at all, and hence there's no conduction of electricity. Now they do dissolve, and these will be examples such as molecular compounds like alcohol and sugar. These things don't break into ions, and so we don't have any conduction. Now sometimes we can be shown by the arrow that's used in a reaction, are we going to have a lot of product or a little bit of product? When we have a big arrow, it means a lot of product. So if we see a big arrow pointing towards ions, that's a lot of ions. If we have a reversible arrow, that tends to mean a limited amount of product, so a limited amount of ions if we had ions on the right side. Okay, let's add some examples. What type of electrolyte is represented in this equation? Well, first, are there ions? And there are. To tell if it's strong or weak, we now look at the arrow, and we have the big one-way arrow, so this is an example of a strong electrolyte. Okay, do we have any ions? No, no ions, so it doesn't matter what type of arrow. This is an example of a non-electrolyte. Okay, I see ions on the product side, and I look at the arrow, which is a reversible arrow, and that means there's a limited amount of ions, so don't expect high concentrations when we have that reversible arrow. And that then means a weak electrolyte. There's some ions, but not a lot. But don't start with the arrow, because as you see, you can have a big arrow or a reversible arrow for non-electrolytes. Okay, next we have net ionic equations, and net talks about a net change. And so as an example, when solutions of calcium chloride and sodium carbonate are mixed, we form this insoluble calcium carbonate precipitate. We might write the reaction out where we would show all of those ions on the left, and then the calcium carbonate and the leftover sodium and chloride ions on the right. Now, as a net ionic equation, we're only going to show what changes. And then do note, the calcium ions change. They're now bound up with the calcium carbonate. Same with the carbonate ions. But the sodium ions and the chloride ions remain unchanged. So these are known as spectator ions. They remain unchanged. They're not part of the reaction. And so as a net ionic equation, we're going to remove them. So the net ionic equation shows the calcium and the carbonate forming calcium carbonate. This shows the change. Calcium carbonate started as individual ions in solution. That's what the aqueous refers to. And then we formed the solid calcium carbonate, and that little arrow helps remind us that this was a solid and fell out of solution. So again, net ionic equations, or net equations, show those species that undergo a change. Now, when you're writing a net ionic equation, the first thing you're going to do is you're going to write all of the formulas of your reactants on the left. And you might do that by, okay, here's one solution, I have these ions, here's another solution, there's those ions. Then we need to identify what the products are, and something may have changed, and we may actually be given that information in the problem, but we might have to go and look up if something forms an insoluble precipitate, and we'll talk about that when we get the precipitation reactions in a little bit. Okay, so at this point we have the full equation. Then we're going to delete any species that are unchanged, our spectators, and then we're going to rewrite the equation if needed, and then balance the equation. Sometimes you can just balance it without rewriting it. Okay, here's an example. We're told a solid piece of zinc is added to a hydrochloric acid solution, and we're told that a hydrochloric acid solution has hydronium and chloride ions. That H3O plus is hydronium, and produces zinc ions, hydrogen gas, and water. Write a balanced net ionic equation. Well, first we write out the reactants, and so we had zinc, solid zinc, and then it reacted with the hydrochloric acid, so that's the hydronium and the chloride, and then it produced zinc ions, hydrogen gas, and water. Now, is there anybody that remained unchanged? Well, what happened to that chloride on the left? Well, it actually would show up on the right, and that shows us that didn't change, and hence chloride is our spectator here, and we would omit it. Now you can go ahead and balance the equation as is, or you might rewrite the equation. And now let's balance it. I see one zinc on the left, one zinc on the right. The least common multiple is 1, so there's one zinc on both sides. Then, well, who should we leave for last? And I'm going to let hydrogen be last. Oxygen next, 1 on the left, 1 on the right. Least common multiple is 1, so there's one oxygen on both sides. And remember, I only want to change the hydrogen when I balance my hydrogen. So I have 3 on the left, 2 in the water on the right, so I need 1 more from the H2, so that means 1/2. My equation is balanced at this point, but it's just not acceptable. I need to clear that fraction, so I multiply the whole equation by 2. Okay, are we good? Well, I see 2 zincs, 6 hydrogens, 2 oxygens, but I also see 2 positives on the left and 4 positives on the right. I can't have that. So what can I do? I can change those zincs back to 1. Our reactions need to be charge balanced as well as atom balanced. Okay, next we're told that aqueous chlorine reacts with a solution of potassium bromide and produces aqueous bromine and chloride ions. Write a balanced net ionic equation. Okay, well, we begin with aqueous chlorine, so that's chlorine, AQ, and potassium bromide, so that's separate potassium ions and bromide ions. And it produces aqueous bromine, so that's bromine aqueous, and chloride ions. And at this point you might notice what happened to the potassium. Well, they would be over there on the right as well. And is there any spectators? The bromides were, the potassiums were our spectators. They remain unchanged. Both the chlorines and the bromines changed. And now we can balance the equation, or rewrite it and then balance it. I'm going to let bromine be last and start with chlorines, 2 on the left, 1 on the right. These column multiple is 2. So there's 2 chlorines on both sides. Then bromine, 1 on the left, 2 on the right. These column multiple is 2. There's 2 bromines on both sides. And let's check the charges. 2 negatives on the left, 2 negatives on the right. So we're good. Okay, often net ionic equations show up in the form of what are called precipitation reactions, and this is when, like that calcium and carbonate that got together and formed calcium carbonate, we are forming an insoluble precipitate. Now, we're going to still start the exact same way with our reactants identified on the left, but when we go to identify the products, we're going to have to identify, do any of the cation-anion combinations form an insoluble precipitate? And there's a table that's going to show us if they do or don't. So again, we'll see if, for example, calcium and chloride were soluble, and they were. How about calcium and carbonate? No, they weren't. So here's an example of a precipitation reaction. And we're already given the reactants and the products, so essentially step 1 and 2 are already done for us. We just need to balance this. Actually, we would eliminate any spectators, but there aren't any spectators. There would have originally been some spectators, but there aren't any now. So the point is that when we mix solutions of silver ion and chloride ion together, we form that insoluble precipitate, silver chloride, and again, do note the downward pointing arrow and the S telling us it's forming a solid which is falling out of solution. Now the table that we're going to be referring to is actually in figure 4.3, which shows you the insoluble combinations by using shaded boxes. Depending on your text, depends on which page number it is. If you have a newer text, it may not be on page 80. But I do believe it's still figure 4.3, so you might want to look at that and see. It showed that silver was soluble with lots of things, but when it came to chloride, it had a shaded box, indicating that it was an insoluble precipitate. So again, when we get to step 2, you're going to have to refer to that figure, 4.3, to determine if we're forming an insoluble precipitate. Let's do an example. We're asked to write a net ionic equation when solutions of barium nitrate and potassium sulfate are mixed. Well, step 1, we write the formulas of the species in solution. So in a barium nitrate solution, we have separate barium ions and nitrate ions. And then in potassium sulfate, we have separate potassium ions and sulfate ions. There's step 1. Now for step 2, we know that barium is soluble with nitrate and potassium is soluble with sulfate. If not, then they wouldn't have formed solutions. But is barium soluble with sulfate or potassium soluble with nitrate? And as we look at the table, we see, oh, barium is not soluble with sulfate, and hence it's forming the insoluble precipitate, barium sulfate. And that's going to fall out of solution. Let's do the same for the potassium and the nitrate, and we see, oh, potassium soluble with everybody, as is nitrate. Now it's helpful for us to recognize that all of our group 1 cations, so lithium, sodium, potassium, are essentially soluble with everybody. That's also true for ammonium. So if you ever see those ions, we know they're going to be soluble with any other anion. And when it comes to the anion, nitrate is soluble with anybody. So if we ever see nitrates, we don't have to worry about looking for insoluble precipitate, just like we see any group 1 cation, we don't have to check. Well, if you forget, then you're going to have to check. So that's why it helps to remember. So again, the potassiums and the nitrates remain in solution, and so they are our spectators. So let's go ahead and scratch them out. And then we might rewrite the equation. That's up to you to decide if you want to rewrite the equation. It definitely cleans up our picture. Sometimes that's what we need. And now let's balance this. And I'm going to count sulfates, not sulfurs and oxygens individually. 1 barium on the left, 1 on the right. The least common multiple is 1. 1 sulfate on the left, 1 sulfate on the right. Again, the least common multiple is 1, and we're balanced. Okay, let's go over what we have learned here today. And in our first example, we're asked, what is the molarity for 60 grams of sodium hydroxide and 0.25 liters of solution? Okay, we're using our units for this, and that's definitely a good thing. So step 1, we're after the molarity. So big M bar? No. Why not? Well, big M bar looks like a single unit. Are we really after a single unit? No. What does molarity actually mean? Moles per liter. You may be familiar with the Newton, abbreviated as N. Is that a single unit? No, that's a kilogram meter per second squared. So you may remember that or know that from a physics class. So some of these units where we have a compound unit, like moles per liter, is abbreviated by what looks like a single unit. So don't start with that big M bar, because then step 2 wouldn't have been done correctly, because we wouldn't have started with 1 unit per another, which is what we need to do. Okay, we have 2 units up here, grams of sodium hydroxide and liters of solution. Which one is going to go on the top and take us to moles of sodium hydroxide? 60 grams of sodium hydroxide. And which goes on the bottom and takes us to liters of solution? Well, we're given liters of solution. Sometimes if you get stuck on the top, ask about, well, we should go on the bottom. Okay, we need to get out of grams, so for step 3, let's put grams of sodium hydroxide across the denominator line. Here comes the big question. Can we go straight from grams of sodium hydroxide to moles? We surely can. There's our most common calculation in all of chemistry. And as we look up the molar mass, we have 23.0 for 1 sodium, 16.0 for 1 oxygen, and 1.0 for the hydrogen, so 40.0 grams per each mole. And that then would be 6 moles per liter. We put a 6.00 to indicate that this answer deserves 3 significant figures. Next, we're told a sample of 50 milliliters of beer is found to contain 3.11 grams of ethanol. And there's the formula. Calculate the molarity of alcohol in this beer. Okay, again, we're using our units, and we're after molarity, so big M bar. Now, we learned our lesson in the last problem. And if we're finishing with 1 unit over another, then for step 2, we're starting with 1 unit over another. And between milliliters of beer and grams of ethanol, which is going to go on the top and take us to moles of ethanol. The grams of ethanol. The milliliters of beer will take us to liters. And now, out of grams of ethanol, here comes the big question. Can we go to moles? We sure can, so that wasn't too tough of a question. Okay, this time we need to get out of milliliters, so place it across the denominator line. And can we go from milliliters to liters? We most certainly can, and we're done. For the numbers, there's the formula. 2 carbons, each at 12.0 grams per mole. 6 hydrogens at 1.0 grams per mole, and 1 oxygen at 16.0 grams per mole, which adds up to 46.0 grams per each mole of ethanol. And 1 milliliter, 10 to the negative third liters, base 10 number still going with the base unit. And 3.11, divide 50, divide 46, divide 10 to the negative third, and I come up with a 1.35 molar solution. We're asked what volume of a 1.5 molar hydrochloric acid solution is needed to provide 6 moles of hydrochloric acid. HCl in water is hydrochloric acid. Okay, we're using our units. And step 1, we're after the volume. So, well, liters would be the easiest unit. And remember what that 1.5 big M bar means. Maybe it's a preliminary step, we might want to pull that out. Okay, step 2, which of these numbers has a single unit attached? Not that big M bar. Again, we might want to pull it out and identify that's 1.5 moles of HCl per liter of solution. And that makes it clear that it's the 6 moles of HCl, the hydrochloric acid, that we're starting with. Alright, step 3, out of moles of hydrochloric acid, can I go straight to liters? Well, the answer is sitting right there in front of us. That's the great thing of having one of those conversion factors pulled out. And it also makes it clear where the numbers go. That 1.5 is going to go with the moles of HCl. It doesn't matter if it's on the top or on the bottom. Numbers always go with specific units. It's never a case of, oh, this number's always on the top or this number's on the bottom. And 6 divided by 1.5 would be 4 liters of solution. How many grams of potassium chloride would you need to prepare a 0.25 liters of 2.00 molar potassium chloride solution? Okay, I've got a calculation before me. Equations are units. We're using our units. And again, I might start by asking, do I have a preliminary step? And how about we pull out that big M bar? And actually, I'm going to show you kind of a lazy way of just extending that bar and putting it over liters. So again, I just extended that bar and put it over liters. Now I can at least see that that's a conversion factor. On to step 1, we're after grams of potassium chloride. Step 2, only one number has a single unit, and now it's obvious that 2.00 big M bar has 2 units. And hence, it should be obvious that the 0.25 liters of solution is what we're starting with. Okay, let's go on to step 3, out of liters of solution. And can we go straight to grams of potassium chloride? No, but we see how we're going to get there from moles. So from liters to moles, using that concentration term, and then from moles to grams. 2.00 moles of potassium chloride per liter of solution. And now the molar mass of potassium chloride, and I go and look up the molar mass of potassium, add it to the molar mass of chloride, and we get 74.55 grams per each mole, or 37.3 grams of potassium chloride. Okay, what type of electrolyte is represented by the following equation? And I see ions, so it's either strong or weak. Which is it? Well, that reversible arrow tells us weak. Okay, I see no ions, so it doesn't matter what type of arrow, this is non. I see ions again, so it's strong or weak. I go to the arrow and the big arrow says strong. So the first one was a limited solubility ionic compound. The second one is a molecular compound, and this is a strong acid. One of our examples of strong electrolytes. And what type of electrolyte are the following? Sodium chloride, a soluble salt. Soluble means high concentrations of ions, so this would be strong. Phosphoric acid, a weak acid. Weak acids are weak. Hydrobromic acid, a strong acid. Strong acids are strong. And let's see, barium sulfate. Well, it's an ionic compound, so it's strong or weak. Is this soluble or insoluble? So I go to that table, 4.3, and look to see if barium sulfate is on the soluble or insoluble. And we see that it's insoluble. The box is shaded. So insoluble means limited. Think of that reversible arrow. So this would be an example of a weak electrolyte. It's going to have some ions, so some conduction of electricity, but not a whole lot. Okay, we're asked to write net ionic equations when solutions of iron 3 nitrate and potassium hydroxide are mixed. Well, first, a solution of iron 3 nitrate exists as separate iron 3 ions and nitrate ions. And a solution of potassium hydroxide exists as separate potassium ions and hydroxide ions. If we have solutions of these ionic compounds, they must have dissolved, which means they must be in solution. And now we know iron is soluble with nitrate. What about with hydroxide? And if we look up iron 3 in the solubility list, we see, ooh, it's one of our insoluble hydroxides. So we're going to form the insoluble precipitate iron 3 hydroxide. And we know potassium is soluble with hydroxide. Is it soluble with nitrate? Well, we already discussed how potassium and all of our group 1A metals and nitrate are always soluble. And so there are spectator ions in this reaction. So let's scratch them out. And we may or may not feel like we need to rewrite the equation. And now let's balance it. And I'm going to start with iron and leave hydroxide for last. I don't have anybody in its elemental state, so one iron on the left, one iron on the right. Least common multiple is 1, so one iron goes on both sides. Then one hydroxide on the left, and 3 on the right. 3 is our least common multiple, so 3 hydroxides on both sides. I don't feel like I need to check, but if something distracted me, I might. 1 iron, 3 hydroxides, 3 hydroxides. Okay, why don't you take a crack at this on your own, and then come and pause this presentation, and then come back when you're done. Okay, let's do this together. Step 1, magnesium chloride exists as separate magnesium ions and chloride ions in solution. If they are in solution, we're told that we have solutions of magnesium chloride and sodium phosphate. So again, they exist as their separate ions in solution. There's step 1, identify the participants that are your reactants. Step 2, we identify the products. Well, we're not told about the products being formed, so we look at our solubility rules in table 4.3, and we see magnesium is soluble with chloride, but it's not soluble with phosphate. So we're going to form that insoluble precipitate, magnesium phosphate. I'm going to draw that arrow in the S to remind us it's falling out of solution. Then, sodium is soluble with phosphate. How about with chloride? And I think we know that it is. And the sodium and chloride ions remain unchanged. So these are our spectators. And I'm going to rewrite the equation. And now I'm going to balance it. I'm going to start with magnesium and finish with phosphate. 1 magnesium on the left, 3 on the right. The least common multiple is 3. Whatever your least common multiple is, that's how many go on both sides. Then 1 phosphate on the left and then 2 on the right. 2 is our least common multiple. There's 2 phosphates on both sides. And we're done. I hope this is what you got when you did this on your own. Okay, that concludes lecture 4.1 through 4.2. where we learned about solute concentrations, and we'll be learning about more solute concentrations in Chapter 10. But for right now, we're introduced to that most common solute concentration term that we use in chemistry, molarity. And I hope you can see why it's the most common, because it gives us a quick and easy way to get the moles. And when we do reactions in solution, we want a quick way to get the moles. We talked about electrolytes. These are species that form ions, and then the ions are doing the conduction. The definition of electrolytes are substances that, when dissolved in water, conduct electricity. Water all by itself is a poor conductor. So just pure water is not going to conduct electricity. We need these ions. And we saw about the three types: strong, weak, and not. Then we learned about net ionic equations, and net means that we only show those species that change. So if we have somebody that doesn't change, that show up on the left and on the right, we omit them. And precipitation reactions are one type of net ionic equation where we get to predict the products using the solubility rules in Table 4.3. And that concludes this lecture.